Thank you, everybody, for coming to our second panel discussion. This one is on performance-based design, seismic, and wind. And we have three great people here to talk about it. We've got two of our experts from DeSimone. One of them is John Vicey. He's the managing principal from our Chicago office. And I believe that you wrote a paper for the CTBUH on performance-based seismic. Our second guest is Jeff Dragovich. He's an associate in our Seattle office. And also he's our expert when it comes to performance-based design in wind. He's also our IT experts, our software experts. Anything that goes wrong in our computers in terms of software and analysis, we go to Jeff.
So he's busy.
And then we have one of our great guests here. Thank you very much, Russell, for excellent. It was our idea that we should get someone who we've worked with and had great fun with, and John has been working with you for a long while, and you was the first name that came to his mind. So thank you very much. Okay, no pressure. Okay. So I won't waste any more of your time. There's going to be a Q&A at the end of the three talks, and hope it's not too technical for you. What we wanted to do is show you the cutting-edge things that we're doing at DeSimone and what you can achieve from performance-based design, and hopefully to bring that more within the DeSimone company. So thank you very much, guys. Thank you.
All right, well, that's the nicest that Lindell has been to me in a long time. We're going to try to keep this talk on kind of a 40,000-foot level, okay? So, you know, like if you have any questions afterward, more than happy to answer them. I mean, when we're talking as structural engineers about performance-based design, typically we're talking about something that's beyond code, beyond prescriptive code. So, you know, normally we'll do seismic design, we'll do wind design, we'll follow the code. It's a very kind of a cookbook type methodology. Today we're going to hit on probably two of the bigger categories that we're seeing, a lot of the trends with PBD and a lot of the newer stuff going on. Performance-based seismic design has actually been around for a while, so there's a little bit longer history. I'll talk a little bit about our experience working internationally with that. And then Jeff is going to talk about some of the research that we're doing right now with relation to performance-based wind design. I also want to recognize there's three other areas of performance-based design we think about when typically as a structural engineer. One would be vibration. If we're doing lab buildings or something, we have a sensitive floor system and we have to go through a more involved analysis and design. Fire engineering. Fire engineering is pretty mature here in the London market, but it's still maybe a prescriptive type design. I remember when I lived here 20-something years ago for a couple of years, did a lot of work in the Bishopsgate area, and a lot of that prescriptive type of code design was built into the design of those buildings around there. But when we think about performance-based design for fire in the US, we're thinking more about taking events and modeling specific events and looking at how the structural system performs. It's typically not on office buildings, it's more on like convention centers, something where you have a higher floor-to-floor height, so you have a better chance of getting it to work and some more efficiencies. And then blast, of course, all government buildings. The three on the bottom, we're not going to touch today. We'll have to come back to London and do that some other time. But Jeff and I are going to hit on seismic and wind. And then Russell's going to bring up a wealth of other things that we didn't even think about with PBD. But
no seismic.
No seismic. Oh, and what I should mention is, you know, some of these things I'm going to bring up from my past work with other groups. But just to let you know that, yeah, it's other, yeah, like, but the currently in our office right now, we have two projects that we're doing as performance-based seismic design. This is a residential tower in Salt Lake City, which is a pretty high seismic design code. And then also a job in Puerto Rico. So this is another condo tower that we're doing performance-based seismic design. And wind. A few years ago, when I didn't have much more hair, but I had a little bit more hair. All right, and I don't get any money from selling these CTBUH publications. But Jeff was involved with this too. And since this was about 2015 or so, we put out this publication. The idea here was there was a lot of performance-based seismic design projects that had been done, and we wanted to show something that was a little bit more helpful with guidance. So there's good examples in this, and I would say that, you know, we present it in a way that developers can read it, architects can read it, and so that they can become a little bit more knowledgeable about what structural engineers do when they approach, and geotechnical engineers, when they approach one of these problems. Now, my background's a little bit less traditional than most US engineers who get involved in performance-based seismic design, because most of those guys hang out on the west coast of the US, like Jeff, you know, like, and they're kind of in that huddle doing a lot of work on the west coast that's very specific to that region of the US. My experience dealing with this issue was really when I began my work at SOM. So when I was in SOM's office in Chicago in the early 90s, they did a lot of work in China, and they started a whole number of different projects there. This was one of the first projects that was done there and used as a benchmark. This is just 25 years later. It's a whole redevelopment of the Pudong district, was the Jin Mao Tower. So this pointer doesn't work, but the Jin Mao Tower was this kind of, you know, like 88-story, very, you know, like repetitive type of setback system. And this was used as a benchmark. And really, you look at this building, many of the buildings that were done that were taller, like Russell, I think you actually worked on Shanghai Tower.
I touched it. I didn't really work on it.
Okay.
It was already designed. I need to give you a new photograph of that.
Okay, well, this was in 2013, and really what it was just meant to show was how much things change and how many projects like this were being done in China. So that was my exposure, and also the whole evolution of the process. What it took to get Jin Mao through the design process and through the expert panel review and the peer review was far less extensive than by the time Shanghai Tower came along. So why would we do performance-based seismic design? Most of the time we're mandated. We have to do it. Within the US, or if you're using IBC, International Building Codes, you know, there's definite limits on heights of buildings and systems that you can apply in a high seismic zone. So in the tall buildings in high seismic zones, or buildings that have unusual structural systems, you know, you sometimes are mandated to use a performance-based seismic design. Also, what it does is it gives us an idea of how to use like innovative technology. It's a vehicle. Sometimes you can't accurately understand a system unless you're taking it through a more involved analysis. If we're talking tall buildings, then we look at what are the regions of the world, where are they high seismic regions, and how do those correlate with large metropolitan centers. And so, you know, the ones that stick out in my experience is Southeast Asia, obviously. And then also the west coast of South America and Chile and Santiago. They're having large scale events on like almost an annual, you know, an annual return rate. So in an area like that, the expectation by the public is not that you're going to design a building and collapse prevention is a realistic goal. You want to be able to walk in that building the next day. And the only way you can accurately assess that is by doing performance-based design. And then also the west coast of the US. And just to give you an idea, this is the Sendai earthquake. I just grabbed this off the internet, 2011. Gives you an idea of like what kind of movements you're talking about with tall buildings. The thing that's interesting about this is many times seismic might govern, not necessarily, if you're in a high region, if you're close to a fault, of course you're really worried about it. But like for instance, if you look in a zone like Dubai, if you look at a zone like Dubai, you know, many of the seismic events that occur in Iran are actually influence the seismic criteria you need to use for design there. And that's not, you know, that's a couple hundred miles away. I don't know how many kilometers. All right, so conventional wisdom, we grade these different structural systems. We say like a bearing wall system is this good in, if we saw a rare seismic event, how well would it dissipate the energy of a large earthquake? How would it ductily respond to it? And how can you, and this is somewhat experimental. This is the current approach for prescriptive design. So you see a time history record here, and whenever you see a time history record or a series of them gets represented in a response spectrum. That's kind of like an envelope of the responses a building could have based on all the ways it could vibrate, okay? And we use these gradings of different structural systems to figure out how we can reduce the seismic loads because the building's going to respond ductily. It's not going to see the full elastic, the full force of the full G's of an earthquake. It's actually going to respond in a way where it's more ductile and the loads are reduced. So the better the structural system, the more ductile it is, the higher value we reduce that response spectrum when we do conventional design. So what are the disadvantages with that? There's a value, that reduction factor is a seismic reduction factor. It's this R value, and it's used in Eurocode, it's a Q value, okay? It's kind of similar concept. And it's qualitative, it's less direct, it's less accurate, and it has less definition of areas where special detailing is required. You just kind of are thinking about those areas, but you don't directly assess where that ductility occurs. There's less freedom with definition of systems. And then you hit something like this. You know, you have a bearing wall system, you read in a catalog, its R value is 4 or 5. What would you even call that? You don't even know, CCTV would be like something that would not even fit into any definition. So there was a quantification document that was put out where they attempted, when computers probably didn't have the same computing power, to define those types of systems that didn't fall into the regular list of structural systems. But by the time you get to the end of all this work, it's almost like now you should just directly assess things. And so what we opt for when we're doing performance-based design is we just take that same time history, instead of going through the response spectrum, we're putting it into a building model that has all this direct ductility of link beams and walls directly modeled. So the building's not responding elastically anymore. It's not a linear approach. It's actually, we're seeing some of those elements fail. They're not failing, but they're cracking and yielding. And that is the actual development of the reduction and the ductility in the structural system. And then we keep track, all right? And then looking at all these elements, there are still some elements when we do the performance-based design where we're looking at them as being force-controlled elements. So those are strength checks, the same way you would do a normal strength check in a building, and that would be like for gravity columns, things that we don't want, to actually yield or see any kind of cracking. But elements, you intuitively think about coupling beams. Those will have a lot more deformation in them, and you'll see a lot more ductility. And also in tower core walls, yielding of the vertical bar, hinging. And that allows the building to respond in a way that's safe and offers, like a good fuse point that we can investigate in detail. When we do performance-based design, it's a two-step process. So usually we look at time history records that are correlated with the green response spectrum, and those are like 75-year to 100-year events. The building is intended to respond elastically. Nothing goes nonlinear. But then we look at the rare events, which are like the 2,000 to 2,500 year event, where all of this ductility is actually developed. And these are, they're similar return periods to Chinese code. So that's why you see all the translation there. So kind of the lay of the land in the US, traditionally prescriptive loads, prescriptive codes deals with these R values, these seismic reduction values. There's height limits for certain systems in high seismic zones. And performance-based seismic design is not just done for new construction when you're over limit. You also will do it for retrofit sometimes, okay? And there's a particular code dealing with that. Eurocode 8, similar prescriptive rules to the US with these seismic reduction values, but they're called Q values rather than R values. And as I know it at this point, there are no height limits for certain application of different systems. In China, there's prescriptive rules to check the service level, and it's a two-tiered system similar to the US system. It's a form of performance-based design for buildings where they're over limit, so they understand a restriction on a particular system being applied in a particular seismic zone. And then it's a nonlinear time history analysis, but the component checks are like they're a little more vague. They kind of just look at areas of interest. They aren't checking component by component. There's good publications that have a long history of being utilized for this. The TBI peer document was, and it steps through a process for tall building design when you're doing the nonlinear analysis. There's also other codes like the Los Angeles Structural Design Council puts out a document that they've kept updated. It's very similar to TBI, but it has a little bit different guidance. And the big boost in this as a design process has been the ASC 7 now. With the version of 16, actually had nonlinear analysis and performance-based design included in it, and now that's been enhanced in the 22 issue. Even though some form of performance-based design was being utilized in the US in the late 90s, this is a classic example of why you might want to utilize a system like this. Because if you do any, similar to probably London, any type of residential tower project is post-tension slabbed with a bearing wall system. You want to limit the number of downturns in the formwork. Any extra formwork is very, very expensive. Now, this would have been a cost prohibitive. This was a restricted system in San Francisco area prior to this, the development of performance-based design, because in order to get a building that would have been code compliant, you would have had to add a ductile frame on the outside of the building, which would have been cost prohibitive. So by doing performance-based design, you're able to get something like this through the approval process. And this is a building did for Samsung headquarters in Beijing. And the thing that was interesting about this is that we pursued the idea of innovative design. So we looked at a couple different options for the client, who was Samsung. We looked at, instead of just using outriggers and a belt truss at the mechanical levels, we actually used an idea of using viscous dampers there. And so what they did was, and viscous dampers are hard to model statically because they only pick up load when there's a velocity. So you really need to take them through a time history analysis in order to see how they'll respond.
So, John, is that a hydraulic system?
Yeah. So they use these systems. This is what they look like. They use them on Torre Mayor in Mexico City. So that's a pretty old building.
Yeah.
But there they were used more just like in the exterior frame in order to get an additional amount of damping. When you look at damping in systems like this, it has the same effect as reducing the seismic load with like a higher R value because you just drop the response. And what we were able to prove to Samsung, who was the client, was that, listen, if we do a conventional steel and outrigger and belt truss system, you see a lot more red there. That equates to damage. It's more damage that you would see for the same seismic event. You'd see the building respond more linearly with the viscous dampers in play. And then another way to illustrate that is you look at the total energy that's dissipated by a rare event. Think about it, the viscous damper system has a longer period of the building, so it actually sees less total energy that needs to be, dissipated in the system. And then also think about the zone under the red here is the energy dissipated by the structure. So that's like, that's walls cracking, bar yielding a little bit, it's damage. It's not damage beyond a certain point, but you still see here, with this system that's more conventional, you only have about 40% of the damage with the damper system as you do with with the conventional system. And then I think one of the things that Jeff is going to hit on is, whoops, let's see.
I thought you
I ruined your
video.
yeah, I was supposed to have a video right here. And it's not going to work. It's Connecticut link beam. All right. So there's this idea now that what we're thinking about utilizing is a viscoelastic link beam, coupling beam, because there's some idea that if you are able to replace, you know, like some of the coupling beams that are working really hard in the system, you can isolate, you know, like where the energy is dissipated and actually monitor it in case there's a rare event and replace those elements if there's a lot of damage to them. So anyway, Jeff.
Excellent. Thank you, John. So what I'm going to talk about now is performance-based design related to wind. So I put this little cartoon together because I'm going to be kind of jumping around a few topics. First one is I'm going to go over a couple definitions just so that we're all on the same page when it relates to overturning moment for wind and what that exactly means. And then I'm going to talk about what is performance-based wind design contrasted to the typical code level design. Then I'm going to talk about a framework for performance-based wind design that is currently coming out in the US. And as we'll see, performance-based wind design has some computational challenges, so I'm briefly going to kind of address what we're doing at DeSimone looking at related to analytical considerations and how to do this work effectively. And then we'll have a brief example of a building that we currently have in the office. And the last question, we're going to do why PBWD, I'm putting that at the end, and John had his at the first, because I think once you look through this, you might have a better sense of why you might do it. Okay, so some definitions. The most important thing about the left figure, it's an elevation of a building, and I just wanted to define the term coupling beam, which is a beam that spans between two walls. And you can see the wind loads go up the building, and if you multiply those individual wind loads by their respective heights, you get something called the overturning moment at the base in a particular wind direction, and because we're going to be using that later on in a couple of plots. And just to kind of summarize what John already talked about, force-controlled versus deformation-controlled elements. And so a force-controlled element is a linear element, and so like the middle cartoon, if you apply a force to a spring, it displaces X. If you apply 2F to the spring, you get 2F. That's a linear response. The one on the far right is something you would see in an element that is detailed and designed ductily, where you load it up to a point B, and then when you unload, there's some area between the loading and unloading, and that's the dissipated energy in the system, which could be a coupling beam or a damper, among many other things. So here, PBD, what is it? Well, what I'm showing you is what it's not. This is prescriptive design. And on the left, I have basically the floor plan. That's out of the ASCE 7 directional wind procedure, which is what you would typically do in a building. So basically, you have all these load cases, and you apply those loads at every floor level, and then you get your overturning moments for that particular wind direction. So if you look on the right, we have something I like to call a stop sign plot. But basically, it's kind of a plan view of the building at the base. The little blue thing is the building. And when you calculate the moments for those various load cases, you kind of get an envelope of the design at the base of the structure. Now, PBD, what is it? I think the most important thing is that instead of applying static loads to the building, you apply wind time histories as developed by the wind tunnel. So on a particular floor, you're going to have at some coordinate picked by the wind tunnel, you're going to have wind Fx versus time, wind Fy versus time, and you're going to have a twisting moment about the center of the building at each level. And the three squiggles on the right there are basically wind time histories for I think it's like 36 seconds. Typically, they're 1 to 2 hours. If it's the top one, you notice how it's below the 0 point. That's basically because the wind is continually pushing on one side of the building. So that's going to be the critical wind direction. So this is the framework that has come out recently. I think the first edition of this was 2019, and this version 1.1 pre-standard came out a couple months ago. I'm not going to go through the flow chart on the right, but the important thing here is to take away that it defines 3 performance objectives, which is, if you look inside the big red box, that's what the performance objectives are. And on this slide here, one of the big things that I think might be interesting to everybody in the audience is they describe something for non-structural elements. Sorry about the equation, but basically it's a way of quantifying how much racking you might get in a building. Let's say you're next to an elevator and you want to limit how much shear, what was the word I said I should use?
Distortion.
Distortion. He wanted me to avoid the use of the word shear. So basically, so distortion demands, and all that equation is, if you take that little gray area and you deform it, distort it, it's basically an average of those little angles. And then the table below is kind of some recommended deformation demand index limits. That's from a document developed by the Applied Technology Design Guide 3, which is specifically at serviceability for wind loads. That's something that's really interesting that's in the pre-standard. There's like 5 pages of the framework. I'm just summarizing basically 3 of them for the main wind force resisting system. It also covers the cladding and some other things. For risk categories, it gives you the recurrence interval for the winds you need to consider. For the performance objective, typically is remain elastic, unless you're at the continuous occupancy, where the new thing in this PBWD is you actually allow some of the elements in the building that you pre-select to go inelastic. So think back to that inelastic curve that I showed a few slides ago. And then the acceptance criteria, middle one is the DDI index, acceleration limits like we typically have done for buildings, that hasn't changed. And then the far right is basically you have deformation limits on specific elements that are nowhere near how much deformation you'd get during an earthquake. It's a lot smaller. Okay, so all that said, I'm going to kind of switch gears here and talk about how you would actually do this in practice. I've listed kind of some applications that are typically used for most US design offices. Perform 3D is used for performance-based seismic design. ETABS is used for routine design, but it can also be used for nonlinear analysis. OpenSeas is something that was developed at Berkeley 30 years ago. That is one of its features is it's fast and open source. And WIRA is something that was developed by Seymour Spence at the University of Michigan for specifically doing like Monte Carlo estimations for wind stuff. So that's a great program. Okay, ETABS, a firm has done a PBWD job, and it took them 1 month to run 5 wind time histories in ETABS. So you can see that we're generally concerned and interested in picking something else that might run faster. So, and then WIRA actually uses OpenSeas as its input file. So if you work in OpenSeas, that's where you want to head. So what we have been doing at DeSimone is, because the wind loadings are such small amplitudes, we have started to calibrate actual experimental data against nonlinear elements in those 3 applications. So one of our consultants was involved in this. This is some wind protocol testing that was done at UCLA. I'm not going to go through the details, but there's about 2,100 cycles. 1.2 yield is like a very small deformation compared to seismic, which might be 5 or something like that. And so they went through various protocols there. And I'm not going to show you a bunch of stuff, but basically, if that coupling beam there on the far upper left, if you were to shear it like this, the y-axis is how much force, and the x-axis is how much it deforms. And you can see that this is actually really excellent calibration for the small deformations considered. And the areas in between those loops is the hysteretic energy dissipation that you can get. Okay, and then, so this work, we just got our abstracts accepted to the World Conference in Earthquake Engineering next July in Simon. I'd just like to highlight my DCE consultants. We've got some very high-end academics that are working with us to kind of accomplish this work. Okay, a brief example. This is a building I'm going to call structure 8B. It's 83 stories in a hurricane region, 74 meters per second wind speed, 166 to me, you know. And then, so since you have 3 time histories per floor times 83 floors, you get 249 separate time histories for each model. Whereas in a seismic, you typically have X and Y at the base. You might have UZ, but typically not. And then if you have 4 critical wind directions, you basically have 996 different time histories you have to input to the model. So there's a major data management, I wouldn't say nightmare, but challenge. And we've developed a lot of custom software to automatically populate the models, convert models from ETABS to OpenSea. So we got a whole suite of software tools that you really need to have in order to accomplish this work. Here are some spaghetti plots, I like to call them, of the calculated response for the 4 different colors are the 4 different critical wind directions, and the little stop sign plot there is the wind tunnel static loads. And that really just compares a 2% damping, which is on the right, against the 3% damping. And as you'd expect, the 2% damping gives you more response. And here is basically a little small subset of one of those spaghetti plots for the 40-degree direction. And this should play, and you can see this is kind of, you can see it's a zero mean wind response, and that's, like what, 10 seconds out of, I think these time histories are 2 hours. They have about 20,000 points per time history. And the last slide, I believe this is the last one, we work closely with Kinetica. Michael Montgomery there has contacted me about 4 weeks ago and said, hey, we got some extra dampers in our lab. And I said, hey, if you send me the Brickle model with the time histories, we'll run it, we'll design some of their VCDs in the building. And the cool thing is they actually, the most critical VCD, they actually took the actual calculated time history demands and they actually tested it in the lab. And so now we're able to get the actual energy dissipation in the lab and compare it to what ETABS gives us. So it kind of gives us a little more confidence that we're doing the right thing.
If you send them 8B.
8B. Oh, oops. My bad.
Less of the private jokes, guys.
Okay.
Okay, pros and cons. I just picked 3. Could be a lot more for discussion later on. Pros, a lot of times when you have a high seismic zone and a high wind zone where they might be very close, the old wind directional procedure would make you design some very sheer, very flexurally controlled walls where you get a lot of shear steel. The problem is if you get a lot of flexural steel for seismic, that's not good. So actually it would make the design worse. So PBWD would allow you to make that. Potential reduction in construction costs, able to consider more innovative technologies. Cons, peer review time, the wind consultant's time, and also is a municipality going to even let you touch this stuff. So that's really it for me. You want to switch spots?
So big arrow, yeah. Yeah, why not?
Yep.
Okay. I'm not sure quite how to follow that. Don't have quite so many weird equations. So maybe I should introduce myself a little bit. I'm Russell Gilchrist. I'm a design principal in Gensler London office. Been at Gensler about 12 years. Initially in the Beijing office, then you're going to see some Chinese projects, and then Shanghai, and then Chicago, and now I'm back in London. These are just some of the projects. 2 of these are in, actually more than that, are in London. Maybe some of these I worked on with John, actually. So these are some of the tall buildings that I'm not actually going to talk about tall buildings, really. They're kind of mid-rise. They're only, I think there's 2 40-story and there's 1 20-story building. But I know a little bit about wind, not quite as much as Jeff, but enough to keep me out of trouble. So for me, I guess performance-based design is slightly less prescriptive for me. It's as an architect. There's obviously a bunch of criteria that we always get when we start a project, and what I think I try to do is to try and utilize as many passive moves so that we're not either, particularly from a building systems rather than necessarily a structural perspective, that we're not trying to get a lot of kit in the building just to kind of mitigate an architectural idea. That doesn't always work, but that's kind of where our kind of starting point are. So, and a lot of performance-based design, as John, I think you mentioned earlier, is beyond code compliance. So I'm actually going to show you 3 China projects, and trying to play around with Chinese code is pretty dangerous because it's pretty prescriptive. And the kind of building code guy does not want to make any decision that's outside the code just because he has a boss, and no one wants to take responsibility for that kind of discussion. So it's kind of difficult to kind of push the envelope. But this is actually a little presentation that I gave a little while ago, but it's actually 3 projects in 3 slightly different places in China. And the reason I think this is quite interesting is that Beijing, Shanghai, and Shenzhen has quite different climates. China's a pretty big country, so Beijing is pretty cold in the winter and it gets pretty hot in the summer. So it's a heating and cooling kind of environment. A little bit like London, I guess, in a way, but slightly more extreme. Shanghai does have you occasionally have to turn the heating on in Shanghai. It's predominantly cooling, whereas Shenzhen, I don't think you'd ever turn the heating on. It's usually pretty warm and pretty sticky all year round. So these are 3 Gensler projects. One of the top ones, the only one that actually got built. Actually, the second one's under construction. So really, I just want to talk about how we approach the design of these 3 buildings, mostly from a facade perspective. As I say, what we like to do at the very beginning, usually working closely with a kind of MEP building systems guy or person, is just, what system should we be looking at given the climate we're in? And John and I actually worked on I nearly showed this project, which was Pearl River Tower, which is in Guangzhou, which aimed to be a kind of net zero building. This is 2004, 5, 6. We didn't actually make it, but I didn't want to show that because I wanted to just sort of track through a few kind of different approaches from an architectural point of view. But we're typically looking, we'd love to use kind of water-based systems rather than air-based systems just because they're more energy efficient and it's also a better kind of comfort condition, but we don't always get to use it, and clients don't always like pushing that kind of technology. But this is a project that I did for Harbin Bank. It was initially going to be the headquarters building for the whole bank. Harbin's a kind of place in northeast China, and this is a bank that's going more national across the whole of China, and they were going to move their headquarters into Beijing. The brief from the client was he wanted the most elegant building in Beijing, which, believe me, is not a tough ask. But we did, typically in China, we do multiple, I think this was option 17 or something ridiculous like that. But he went for this one because it looked like a bulging wallet to him. He's a banker. So he kind of liked that idea. But I was trying to put together a more sophisticated argument, but I was quite happy that one way or another he liked it. So what's interesting, okay, sorry, I didn't realize the slide was coming up, but these are just the kind of you can see the little kind of humidity graphs, just the kind of different climates and the 3 different zones. So I hope Harbin backs up first. So this is the plan of the building, and actually it had, let's talk about air quality in China, okay? So that's a good day in China. I was in Beijing for, I think, a day short of a year. I think I saw blue sky on 4 days and through a full year. That was probably the worst day I ever had, was the one on the top right. But pollution is a huge problem, or at least it was. It tends to go away when they're holding a big major event like G8 or G20 because they just shut down factories for 2 months beforehand. But climate and also environment played a big role in terms of how we approach the facade design. And you can see this kind of elliptical twin core arrangement. The outside skin is actually single glazed. So apart from a few custom pieces that we actually had to bend, or have curved glass, all these other, most of, like 96% of it is flat panel. And the inside is double glazed, but the inside is actually faceted, so we could just use standard double glazed units. Because a lot of these great architectural ideas usually get value engineered, so we're kind of trying to think ahead of the game. And the idea was that there would be a blind system in the cavity, which they actually have. So on sunny days, on those few sunny days in Beijing, an automatic blind system, it's actually the same system we deployed on Pearl River Tower. There's a photocell on the roof, so it tracks the angle of the sun. And then if the sun hits the facade at any given point, this is east actually, this is kind of west, then the blinds will come down on any given point where there's a kind of incidence of any kind of solar gain or whatever. Now, the interesting thing about having a slightly curved facade is that the whole facade wouldn't necessarily attract the blinds coming down, so we'd still get daylight. And the idea was that in the summer, the blinds would come down so we didn't attract the solar gain. But in the winter, it does get very cold, and occasionally they do have days like that occasionally. We were trying to trap the hot air in there. So the blinds would have been up, and we're trying to trap that air in the cavity so that we could put it into the air handling unit system so that we could actually pre-warm the floor space. So it's pretty sophisticated. We didn't get very far because the code officer wouldn't allow us to do. He considered the cavity to be an atrium, and in Chinese code that then attracts a whole kind of atrium code. So we had to fire stop every single level, every 4 and a bit meters. We had the sort of thick glass that you could walk on because we had to kind of access the cavity. It's about 900 millimeters wide. So it's quite a kind of sophisticated idea in terms of performance-based design, if you like. So we did a lot of summer and winter analysis trying to figure out how this would all kind of justify itself. So this is a kind of winter condition and a summer condition. We talked about having a winter duvet and a summer duvet. You obviously want more TOG in the winter than you do in the summer. So this was the idea that in the winter we would try and heat up this cavity, whereas in the summer we're obviously trying to keep the hot air out of the cavity, or if it's in the cavity, we're extracting it out or getting rid of it. This has been built, by the way. So now this is the second building. This is in Shanghai. Slightly different context in the sense that I hope I've got a site plan. Yeah. So it's right on the river. It's quite a narrow, we had quite a narrow plot area to actually build something in. The view to the east is not so good. The view to the west and south and north is the Huangpu River, which actually Jinmao is kind of like down here, the project that John showed. So what we were trying to do is really optimize the view to the river as much as possible. So this, again, it's not just building systems, it's about what is the occupant experience in the space. So we wanted to give people as many people as possible a view of the river. So we actually had an offset core that we placed on this eastern side, partly because that allowed us to maximize the view, but also it's shielded or mitigated the kind of less good views to the east. And you can see in this diagram what we were trying to do in terms of, it's not a particularly tall building. I don't consider 140 meters that tall. It's not really, it's mid-rise, isn't it really? It's kind of, but we had a slight step to try and acknowledge the other, it's certainly the tallest building in that particular part of the river, but we did a kind of lower step to try and acknowledge, again, the kind of scale of the other buildings. And again, we work very closely with a guy called Peter Simmons. He's ex-Arup. And he's actually independent now. He actually lives in Holland. He did have a practice in LA. He did a lot of our energy analysis. So we kind of give him kind of crazy ideas about, fixed shading, and then he will analyze it and say, well, this is better than that and whatever. And just in terms of, again, trying to optimize performance through the architecture. Again, there's no kind of active system like Beijing. This is purely passive approach to how we might keep the sun out and keep the building cool. The other part of keeping the sun out is actually still to try and maximize natural daylight. So it's a kind of weird trade-off because in China, even in Shanghai, there's a lot of dull overcast days. So that, we develop all this solar shading, but actually we only ever kind of really use it on certain days of the year. So it's kind of interesting. So again, obviously with the offset core, we've got no sunlight or daylight coming in from the east where the core is adjacent to the floor plate there. The two ends actually do have daylight, as you can see from the plan here. So again, we're just always kind of playing this game between what is the building envelope, what are we trying to do inside, and what are we trying to keep out from so that, you know, the building systems are not blowing their bags out trying to keep everything cool. So again, lots of discussion about floor to floor, what services we can kind of thread within that, what different systems can we use to be able to kind of optimize. In China, you'll probably be aware that they have refuge levels every kind of like 10 floors. You have to have from memory, your first one has to be within 50 meters of the ground plane, and then you can go a maximum of 10 floors before you need another one. So even in a relatively modest building like this, 30-story, you still have a couple of, and from a structural point of view, that's typically where we would put any outriggers. Yeah, he loves them. And so this is called an area of refuge, which is typically only a fraction of the floor plate, and the rest of it will usually, typically, there'd be an outrigger system that would connect to the columns and the perimeter, but also all the mechanical plant would be zoned in those areas too, because it's obviously a smaller floor plate in terms of what you can do in terms of occupancy. This is just a couple of visuals of what it looked like. I should have a finished photograph, but I think it's sort of only partially complete. Then again, this last one is, again, 162 meters, 35, 40 stories. This is, again, down south near Shenzhen. This was actually going to be a building for the local planning office. They were going to occupy the full, Shanghai has just exploded. Well, so is Shenzhen. I mean, that part of, Shenzhen was a small fishing village like 40 years ago, 14,000 people. It's now got 18 million people. So there's pretty rapid growth. So this was interesting both from what we tried to do with the facade, but we had this rather awkward site that's in the corner. So we weren't actually quite sure how we were meant to respond to all the buildings and how we responded to the urban edge. You can see, look how many road lanes there are here. So this presented a kind of tricky dilemma for us in terms of, do you do a circular building, do you do something elliptical, do you do something non-directional? So the way we dealt with that was, again, and for us this is still performance related, I guess. It's slightly less mathematical, I guess, but you know, what do you do? Oh, there was also a kind of very common in China, high level kind of walkway that usually connects the first and second floor to all of these buildings. We actually designed this building as well, Gensler. So we kind of looked at what would be a good response in terms of how do you turn that corner? How do you respond to your neighbors? And the option that we came up with was actually this idea that picked up on the face on the two streets, but also responded to the kind of corner site. So, and that then actually threw up a number of kind of different kind of approaches to how we would treat the facade. This is purely a kind of passive system here. This is just literally kind of a shading system on the outside of a building. And again, we're working with a guy called Peter Simmons to just try and optimize what the fins or what the shading should be, because usually early morning, the east sunlight and the west sun, at setting sun, we tend to kind of develop vertical shading. But on the south side, we tend to go for more of a horizontal, because particularly in this part of the world, we're nearer the equator. So the sun midday is directly overhead. So you don't actually need much of a shelf to actually shade the facade. So whereas on the west facade, you need more of a west and east facade, you need more of a grillage. So we went through a number of kind of iterations. We didn't do 996, I have to say, but we got pretty close. So that is very quick kind of troll through just some building ideas. They're all kind of sort of the similar size, but just the response, and part of it's climate, part of it is just location, and part of it is just how do you bring all of these things together. I think one of the interesting things about John and Jeff's is it's a calculation and it's finite, whereas this thing, architecture, we're tending to deal with lots of things that we're trying to pull together and make fairly coherent. And sometimes when you've got kind of tricky clients, it's not always possible to kind of lasso them all together, but we do try to do that as much as possible. So I'm not sure if that's the last slide or not. Oh, I've got a few more, sorry. I think I'm nearly there. So these are, again, what we, the facade typically, and this is just, this is code in terms of typically what the energy usage is. The facade is obviously, a big aspect of energy in terms of energy consumption. So what we were trying to do with the various building systems was to try as much as possible to kind of reduce the amount that's on the facade, because it's usually the biggest load. So, and again, this is just a system whereby we're talking about basic kind of building systems in terms of what should those MEP systems be. We always try to go active beams, radiant ceiling. Sometimes in humid climates that's quite tricky, but and usually people don't want to do it, and we end up with some kind of level of air system. But we have managed it now and again. Pearl River Tower is actually a water-based system. It's 2 million square feet of water-based system, so much more comfortable. So again, these are just some of the kind of things we look at, and sort of energy use index in terms of what we can do, how the architecture can mitigate some of the energy use that we're using, but also kind of start to form some of the richness and texture of what the building looks like. And we don't typically separate those two out. Oh, I had one more slide, but it's disappeared. It's gone, been edited. I think it was actually an image of the Pearl River Tower, of the Beijing project. I don't know how I got there either. Did I do that? Oh, I think I've been timed out. That's me.
Thank you very much. That was very interesting. And I hope it wasn't too technical for the non-engineers and technical enough for the engineers, so you can ask a lot of questions. Russell, I'd like to say thank you very much for your talk. It's very, very comprehensive. And I'd like to ask a couple of questions so I can start the Q&A. And in terms of performance-based design, in terms of architecture and cladding and facade, how would you approach that in the UK? And would that help sustainability in terms of designing to, reduce the carbon emissions, et cetera, et cetera?
Yeah, I think in a way, in the UK, I don't think it would necessarily be any different. Actually, there's a building not far away from here, 88 Wood Street, which I did when I was at Richard Rogers, now RSHP, I have to remember that, where we did a sort of double facade system. It was, the Harbin Bank is externally ventilated. This one was internally ventilated, and this is 1994, so this is, 30 years ago. The facade, as I'm sort of suggested in some of those pie charts, is a big factor. So I think, and we're moving away from kind of all glazed facades these days, just because it's just too difficult to kind of keep them under control. So we're tending to the proportion of glazing to solid now is much lower than maybe it was 10 or 12, 15 years ago. So there's a kind of aesthetic kind of approach there, but there's also a performance one there, and we're forever mindful. And a lot of this actually, I think, is coming down to passive design to try and minimize in here, the exposure of south-facing facades that will attract, a lot of solar gain. So I don't know really. I don't. In this case, the approach to design is not necessarily geographical. The approach to design is trying to kind of mitigate what those energy loads might be, wherever that is. We actually did do an exercise on the Pearl River Tower. I keep referring to it. I should have put an image. Actually, there was an image at the very beginning. We actually moved that building around the world. We put it in Peru. We put it in Zurich. We put it in Delhi. I think we put it in. It was in Guangzhou, and I think we put it in Melbourne or somewhere, Sydney. And it was interesting to see what we needed to do to the building design to respond to the various climates. So, I mean, there's quite significant adjustments that you have to make. So the kind of design and form of the building had to kind of respond accordingly. We didn't actually do a solution to the climate, but what we did was we analyzed where it was actually performing least well. So that was interesting. I think we did one in Bolivia, which is quite high. So what's Bolivia? 6,000 feet above sea level or something. So there was a lot of cool wind up there, which helped a lot. So using that kind of, what nature gives you is always a good starting point.
Excellent. So when you went to these different sites, you were along as well personally?
No, it was a desktop study,
Oh, no.
unfortunately.
John, there's a saying that PBD designs the building more accurately. What's your thoughts on that in terms of code prescriptive?
Well, I think it's, generally speaking, I think seismic design is probably the first building that you do, that you take through this full-blown analysis. You're a little bit skeptical about experts' extra checks they may be having you do through the peer review. And I've actually, my experience, working in China in the beginning was there were very prescriptive type checks that experts were asking us to do. And generally speaking, you were pretty skeptical about feeling like you had to jump through hoops to do all these extra things. But in the end, a lot of times they actually worked. They were actually, you found when you put the building through a full nonlinear analysis, the response was good and it behaved well. And that can only come from experience. So it's like garbage in, garbage out. If you start out with a bad concept, you have to start to become intuitive. Like it wouldn't be, Jeff and I were when we were working on the Salt Lake City job, we actually had an issue originally with the building because the core wall wasn't yielding. It wasn't producing a hinge in the way that we wanted to produce a hinge. And as a result, it was actually over reinforced. So we weren't getting enough yielding and we weren't developing that ductility so we could drop the seismic load. So part of our process in the beginning was just under reinforcing it, trying to pull bar out so that we could get it. And you only develop that kind of knowledge if you've done a few of these type of jobs.
Okay.
Yeah, stronger is not better.
It's not always better.
Not always better.
Yeah.
Yes.
And that brings me nicely to your question.
Mm-hmm.
I did have someone coming, but I think he's still playing golf or drinking. And his question was in terms of accelerations in cores when it comes to doing PDD at wind. Do you find that the accelerations comes down and you're stripping out more reinforcement, or is it a hit or miss?
You're talking about wind design, right?
Yeah,
so
wind design.
The acceleration approach to occupant comfort is still the same. So when we go through the 700-year MRI earthquake, we're not even calculating accelerations in the building.
When you say MRI?
Mean recurrence interval, yeah, so the wind tunnel will tell you what they think the accelerations will be. And they will compare it against acceptance criteria. So we actually haven't been looking at accelerations calculated for the 700-year event because you're probably more concerned about the building creaking and things like that.
Okay, good. So I'm going to open the floor now to anybody who wants to ask any questions. Don't be scared, okay, in terms of these muffins. You? Okay. Neil.
This might be a stupid question, but I've got one. So you're trying to make the buildings more ductile. Can't you use a more ductile material than concrete, like steel, to design the buildings? Would that help? Or?
Well, I think, I think it's just spending more time with the zones where it's intuitive, where you want to develop that ductility, just studying that area better. And I think, reinforced concrete core walls are if they're detailed properly, you don't want to jam them full of bar, and you want to be, a lot of the checks that you have to do is you have to do those checks up front. You have to set the concept right. Thicknesses need to be right early on. Otherwise, it's the same as doing a wind tunnel. If you go to a wind tunnel and you're like, oh my God, like all my wind tunnel loads doubled or something like that, intuitive, you probably set the concept wrong. You shouldn't be that surprised and stuff. So I find like dealing with traditional material, if you just spend more time in the detailing of it and understanding the detailing of it, there's been a lot of study now recently on timber, hybrid timber. And one of the issues that you think about when you're doing hybrid timber is that, and it stuck out to me, is on the West Coast, they're doing a lot of projects where they might be taking like landscaping off of a garage. And because it's so light from a seismic standpoint, they can add like something ridiculous, like 8 stories of office building or something like that if it's hybrid timber. So I think in situations like that, it's very obvious because the seismic design allows you to take advantage of the fact that the building doesn't weigh as much. There's a real opportunity there. So using material is important there.
But with a timber structure, you've got more columns typically on the stands up.
Yeah. I mean, or you have a bigger allowance for floor.
Yeah. Floor to floor.
Some of those CLT panels can span 25 feet.
Yeah.
They're
But you're typically restricted to 30, 33 feet or something in both directions.
Yep.
Question down there. Question? Anybody else for questions?
I'm not a structural engineer, but I'm curious, those massive dampers you showed earlier, what's the lifespan of those? Do they have to be replaced at some point, or?
Oh, if you're talking about the viscous dampers?
Yeah.
There was some discussion about whether or not we could also, like harvest the energy related to the, like the heat that was produced by that. It would be the same as you traditionally would think with like, for instance, some of these tune mass dampers that they put up in buildings where they have the big mass moving, they still have a viscous damper system engaged on those elements. So they need to be monitored, they need to be checked, you need to have a very definite maintenance and monitoring system in place when you're looking at those. You have to go in, you can't just have a system that you prescribe and depend on it and then walk away and say, it needs to be the owner needs to sign up and be on board with that maintenance scheme.
Presumably you need to keep the fluid in there.
Yeah, you need to keep it, you can't be burning
dry
up.
out.
Yeah, the nice thing with those VCDs is you can actually pop them out, unbolt them,
Yeah.
the coupling beam ones, and take them out after an earthquake and pop a new one in. It's like a shock absorber in a car.
Yeah.
Yeah.
I think the Connecticut link beams, there is a real, we've even found in Chicago, there have been a couple different projects where they've tried to utilize those, where they're really slender buildings. And one of the big advantages and selling points that they have with the viscoelastic link beams are, you put them into a building, you replace 5 to 10% of the link beams that are working really hard. The damping goes way up, and as a result, the wind loads go down, and as a result, you can get like that penthouse where instead of putting a blow-through floor or a big freaking damping system, you can sell it. I mean, that's the prime location. You know, and that's one of the selling points of that. You kind of think about that added expense versus having that floor area to be able to sell.
Maintenance.
Yeah, yeah. But those viscoelastic, those Kinetica beams are just like they're like an inspection thing. They're probably less than the viscous dampers. The viscous dampers take like real maintenance.
Anybody else for a question?
Happy hour. I think it's happy hour.
Yeah, question for Jeff. You mentioned the number of simulations you have to do for the performance-based wind design. I was just wondering what it was that, when you're working on a project, what would decide whether you would go through that process at the moment, and how you see that changing over time in terms of the type of buildings that you would apply that methodology to?
Well, I think up front, there probably you have to understand if the jurisdiction would even consider you doing it, because it's a pre-standard. So it's kind of like with the way performance-based seismic design was, what, 20, 30 years ago? I mean, it's cowboy country, right? And a lot of people in the industry are saying the pre-standards might be a little bit premature. So I think, you know, it's an owner decision probably. Do they want to even spend the money to even consider it? Because if you have a jurisdiction that says, I don't care what you do, you have to meet ASCE 7, you know, overturning base moment envelope, and, you know, I think it depends project by project and by jurisdiction, for sure.
And do you see that changing over time? What sort of time do you see that changing? As it becomes easier for you guys to do that as well?
So my only frame of reference is the Seismic, because I worked at a firm that was one of the first on the West Coast. And so early on in the late 90s, we had a consultant that prepared our own, like John had mentioned, early on, firms kind of held their secrets to their heart, right? And they would go and do these projects and find cities that would do it. Like Seattle was one of the first that would even consider it. And then once it started happening, I think engineering firms realized that they kind of needed to develop the peer document in a LA tall building, and they kind of flipped it so that we got to share our trade secrets. And so I think we're really way back in the, I hate to say Stone Age, because there's a lot of very, very brilliant people that you can see in the Journal of Wind Engineering that have been doing this stuff for 50 years. So it's kind of in this weird place where it's actually being considered by firms. I mean, just the fact that ASCE 7 has a pre-standard is huge. And I went to a workshop at, yep. Oh, I'm sorry, American Society of Civil Engineers. You know, they pretty much do like the loads code. They do the seismic rehabilitation code. They have codes on cable structures. I mean, they do a lot. There was a workshop in Reston, Virginia in March, sponsored by NIST, which is the National Institute of Standards and Technology. And the whole workshop was bringing everybody that does PBWD to date. And we basically walked away. And it's kind of like going to graduate school. You think you leave dumber than you came there. It's like, I mean, and the biggest thing that came out of it was the cladding design for wind was like, it was such a huge deal because it's almost like a proprietary system, right? And they don't want to like share their secret. Yeah. And they do some American Society of Testing for Materials. I always forget. Anyway, they have some tests they have to do, but it's a very closed proprietary system. So we're kind of at this weird place where people are kind of showing their cards, and hopefully in the next 10 years it'll be more commonplace.
So I got a question from online, and I think I know the answer to this, but I'm going to ask the question. Is performance-based design always more cost-effective compared to conventional methods?
No, definitely not. And so, you know, sometimes you're surprised, you know, with the performance-based seismic design, every once in a while you'll hit a record that's causing you a lot of, you know, you're supposed to take a building through 11 sets of time history records, and, you know, a lot of times you're at the mercy of a geotechnical engineer. They'll come up with these set of criteria, and these are the time history records that you're supposed to take into account, and there's supposed to be an element of randomness to it, but there's a judgment call on, you know loosely you're trying to match it to a particular response spectrum, but what I should have probably shown was that that response spectrum is nice and very linear and curved in a certain way. The time history record, when you trace on top of that, is jaggy all over it, and they're all a little different like that. And so every once in a while, you'll hit a record that will be problematic, and the whole design of the system may be suffering as a result of one set of time history records. Now, by code, you're allowed to throw one out, right?
Yeah, there's some provision.
There's provision that allow you to throw it out. There's also a series of discussions you have with the geotechnical of like, why did you stick me with this?
Yeah.
So there's a negotiation with that, and it takes like real judgment, but there are every once in a while, if you have, that's why we would say too, if you pick a bad concept and then all of a sudden you're trying to force it to work, you could find doing a prescriptive code would have been cheaper.
I
Thank
think,
you.
architecturally, I think I would argue that it is effective because what we're usually, and maybe not capital costs, but running costs, because what we're trying to do is develop systems that maybe, 3-4% more expensive, but over 10 or 25 years save you, 14, 15% on your energy bill. So, because again, it's not a direct relationship, it's actually, and quite often we have to demonstrate that to be able to persuade a client to be able to pay that additional premium.
I think early on the big motivation for performance-based design on the West Coast was the 240-foot height limit we have in the
Right.
States,
Right.
where if you have a core wall only, you cannot go above that. And
Right.
so they used to require what's called a backup moment frame, which used to wrap the perimeter with these giant columns and these huge deep beams, and all of a sudden you lose parking spots, which I don't know how much they rent per 10, 20,000 a year, I don't know. Then you have these giant deep beams that cut out the view. So, up front it might be more expensive, but down the road I think the owner probably gets more leasable space longer. So if you do the time value money, it might eventually
More daylight.
they might cross the cost versus the return.
Okay, that actually brings me on to the.
Can I add a question to that?
Yeah, go.
So, in terms of the cost effective, I understand. In terms of being cost effective, I understand in terms of the seismic, because sometimes it's not possible to design a building following the codes because it simply doesn't work. But is it the same answer if it's wind, performance-based design for the wind as well, or it can be, the building can be more efficient if you use performance-based design for the wind?
Yeah, I think if it does allow you to, if a jurisdiction would accept lower loads because you did a PBWD, consequently you might have slightly thinner walls, and you could get an economic advantage. But I think I only know of one building in the States that's been designed in construction with PBWD, and I think they had 5% reductions claimed on construction costs. But that's pretty much the data point I have.
Yeah, no, I mean, when we've talked about like the driving force behind it in the U.S. at least seems to be the idea that, performance-based seismic design was being done on buildings that also would fall into a high wind climate. And so, you would go through the whole process of coming up with a system that works really well and is tuned well for seismic. And then all of a sudden, you find you put the regular wind loads on it, and it's actually governed for wind load. In certain portions of the building, you end up having to stiffen the building up to work for wind, and you have to go back and chase your tail to get the seismic to work. So it creates a problem. There's that, that was the inspiration for some of this, because I think, there was the idea that you already had nonlinear analysis for, for seismic. But then you can see, just from what Jeff was talking about, the data management is just incredible compared to this. It makes the seismic data management, which is still, all groups that are doing this type of work have like a R&D group that can handle all that data management. Otherwise, you aren't doing these
Yeah,
types of
I wouldn't
projects.
consider doing a PBWD. You know, as engineers, we love Excel, right? I mean, we have Excel sheets to do everything. You could not possibly do a PBWD with Excel.
You'd hit a button and it would lock up everything.
Yeah, because you have to kind of think about using SQL Server databases and kind of a more comprehensive, larger scale data management.
John, can I give I'm going to stray into your territory here, so you might have to bail me out. But on Pearl River Tower, we did a project there, which was 70 meters wide, 310 meters tall.
And we actually did that together.
We actually, but we actually put 4 holes in the building as
Yeah.
well. And I don't exactly remember the exact figure, but the comparison between having no holes and 4 holes was like a 12% reduction in steel. So
Yeah.
just because there's less of a sail effect, because the no holes was 70 meters by 310. The holes in there, which we put wind turbines in as well, actually reduced the horizontal lateral wind load.
Yeah,
on the
and
building.
that was because of stagnation pressure. Okay, so if you think of a rectangular building as a rectangular block, the wind hits the broad face and it has to
You get
then
negative
come around
pressure in
the
the back.
corners. And so the pressure in the back is related to how far, like you have to move that wind load on the broad face wind. You start to put decent sized holes into the building and it's far less width that it's working around. Now those holes have to be at least a certain size.
Yeah,
but,
they were quite
But
big.
what we saw, in that situation, it wasn't just like, oh, I'm putting an opening this big for a wind turbine and I don't have that wind sail. It actually had a much more dramatic effect in dropping the pressures.
But John, would you call that PVD design or just clever design?
I just call that clever. Yeah.
So
That was.
I've got another answer. I've been told that time. Just look, one more, last one. This is from online again, and it's part of what you were talking about, Mohammed. Can you please comment on the benefits, the economics, bid process, change order, obviously from the US, constructability issues, etc. Do you include a contractor in your DB process?
Well, I think that we haven't really broached on this topic, but you did bring it up a little bit. The schedule becomes a major issue because obviously when you're doing any of this type of work, the schedule up front, there's a lot of review that has to occur. Like, generally speaking, if you're working on a building in China where you're doing, and it's similar to what we've run into and we've been doing in the U.S. is by the DD phase, your structural system has to be pretty locked in.
Yeah.
And with the U.S. projects, the code is much more defined and comprehensive about the calculations you need to prepare. So, there's still plenty of calculations and design calcs you have to do in the CD phase, but really the system is set by the end of DD. So from a contractor standpoint, I think, they have to address the fact that, the schedule lengthens out towards the beginning of the project a little bit in order to do all this involved design. I can also say, if you've done a few of these projects, you do find areas that as you get deeper into the design, there's a little bit more of a, a little more detail that you have to do. And so, maybe if you're running a design where everything, preliminary estimated quantities, your feet are held to the fire, there might be a little bit of adjustment, when.
And there are some rule of thumbs that are used in preliminary design, like, when you do a PBD job, you eventually have to run the MCE, maximum considered earthquake analysis, which is a full nonlinear model. It takes forever to build, and you got to post-process the results. But a lot of times you can run your typical, design 475-year return period earthquake and say, I'm just going to multiply the wall shears by 2.5, to kind of get close to what the MCE is going to tell you,
Yeah.
and check the thickness and the shear stress. You know, if you're at 4 square root of F prime C shear stress, you're probably going to be okay. So there's
You've
a lot
lost
of...
me.
Yeah. Well, no, basically what Jeff's trying to say in English,
English.
is, like, there are rules of thumb. So in other words, you know that the wall thickness is going to be based on this rare level earthquake. And there's going to be I'm going to use the word shear, but there's going to be a shear force in the shear wall
It's a distortion.
that you can't get around. You know, like that's a force. And although the wall can be designed to have the vertical bar yield in particular places, the shear force, it has to be designed for strength. Now what we do is we have these rules of thumb of things that we can do up front to make sure we got the wall thickness specified correctly. But what we're always doing is going back, and once we've done the full nonlinear analysis, back checking ourselves. You know, did we do that right? Can we tune the bar a little bit? And you know, job after job, you start to get a comfort level of, you know, hey, maybe I should have multiplied it by 2.4 instead of 2.5, you know, and I would have gotten a more accurate wall thickness. So it's all stuff you put into a toolbox.
So I'm going to stop you there, Joe. Sorry. Beginning to. So thank you very much, Russell, Jeff.
You're welcome. Yeah,
John.
That's great. It's fun.
So can we give a big round of applause for Russell and Jeff? So we have an open bar, food on the terrace. Let's enjoy the sunshine before it rains. Thank you very much, guys.